So I'm Ben Mikek. This is joint work with my advisor, Chirun Zhang at Georgia Tech in the US. And I'll jump right in. So first, SMT constraints. This might be a new concept to some people. These are constraints that encode first-order logic problems. It stands for satisfiability modulo theories. And these have a couple of uses in the world of compilers and in LLVM in particular. So among those is symbolic execution. So engines like KLEE that are built on LLVM, they work by converting paths in the program into constraints and then using an SMT solver to solve them to cover all of the paths in the program. There's also a project called Alive that's been published in several conferences that uses SMT constraints to verify LLVM optimizations. And so these are just two examples of ways in which SMT constraints are relevant to LLVM and compilers in general, but there are many others. There are lots of advanced solvers for SMT constraints. Z3 is probably the most famous, but there's also CVC5 and some others. And there's a standard language for representing SMT constraints, and that includes theories for bit vectors, which in the compiler world we would call integers, floating point numbers, mathematical integers, real numbers, and so on. So I think the easiest way to motivate my talk is to start with an example. And so I'm going to start with this example SMT constraint. And this asks whether the multiplication of two integers, a and b, can overflow subject to some division constraint. We'll go into much more detail about this in a second. So what we're going to ask together today is whether this constraint is satisfiable. This is kind of a complex question to answer. We have to think about all of the semantics of the way bit vector overflow works. There's some bit extension in here. There's a multiplication, a not. But I'm going to try to break it down a little bit so that we can jointly understand what's going on. So the first constraint here, that's the one on line 5. What's going on here? We have the two variables a and b. I've shortened the bit widths for the sake of presentation. We zero extend both of them. Then we multiply. And then we extract the upper half of the result. So if overflow happened, then the upper half should contain some bits that are set, and it won't be equal to 0. And if it didn't happen, then it will be. And don't forget that there's a not in front of this that negates this assertion. Then the second assertion, we have this hex f value. You can think of that, that's like the maximum integer. It's 111, right? And so we're taking the maximum integer divided by a and checking whether that is greater than or equal to b. So in some sense, you can think of this as we're checking whether the result of a times b is less than or equal to the greatest integer. And so that's going to be true if the multiplication overflows. The first constraint is going to be false if the multiplication overflows, and vice versa. So these two constraints contradict each other, and the constraint is unsatisfiable. So we've gone into the weeds a little bit to answer this question. Is the constraint unsatisfiable? The answer is no. But the problem is that the SMT solver Z3 takes about 10 minutes to do this. So congratulations, we've all just outperformed Z3 today here. But so this leads to the question of, can we do better than this? Can we do better than Z3 taking 10 minutes to solve this constraint? And in the rest of this talk, I'm going to explain that yes, we can and how we do that. So to do that, let's look at another constraint. This is a very simple constraint. I think you'll believe me when I say that Z3 can solve this constraint almost instantly. But the important part is that it's actually equivalent to the constraint we started with, right? They're both unsatisfiable. And Z3 can tell us that. The first one takes 10 minutes. The second one can be solved pretty much instantly, 0.02 seconds. But they're both unsatisfiable. And so in an ideal world, what we might like to do is to be able to transform the first constraint into the second constraint. So if we had some magic process that let us do this, that would be great, right? And in the rest of this talk, I'm going to suggest that the contents of this black box, they exist, they're possible, and they already exist. And I think it will be no surprise, given that we're at the LLVM developers meeting, what might go inside this black box. The answer is, of course, LLVM. And so the process that I'm going to propose today is we start with an SMT constraint. We do a front-end compilation into LLVM IR. Then we apply the existing LLVM optimizer. And then we do back-end code generation back into an SMT constraint. And at the end, we end up with a much simpler SMT constraint that has the same semantics as the original. So it's either sat or unsat, the same as the original. But hopefully it will be faster to solve because we've applied the LLVM optimizations. And the important part is this difference in the speed up. So when we start out, it may take a long time to solve. When we finish, it's going to be faster to solve, and we'll have to offset that against the time it takes us to do the translation and optimization. To motivate this a little bit further, I've here listed some of the elements of the SMT language and LLVM IR, and you'll see there are a lot of things in parallel. There are some slight differences, like LLVM only allows some fixed widths of floating point numbers, whereas in SMT-lib, they can be arbitrary. And there's some other slight differences in operations, but for the most part, there's a lot in common, and this is kind of the observation that led us towards this work. So we've implemented this as a tool called slot, SMT LLVM optimizing translation. The front end works quite simply. We just traverse the syntax tree of the SMT constraint and convert each operation into an LLVM operation one by one. Most of the operations actually have one-to-one equivalence, as we saw in the table on the previous slide. So for example, there's a BV mul operation that gets converted into LLVM multiply, same for addition, same for floating point operations. But there are a few expressions that are more complex and don't have direct equivalence. And there are some operations that are defined in SMT-lib, but can lead to undefined behavior in LLVM. So we'll have to handle some of those special cases. There are a few important challenges to this. So I mentioned we have a front-end translation and back-end translation. Each one of those needs to preserve the semantics so that we end up with a constraint that's that has the same satisfiability at the end as where we started. And because SMT constraints are used for a lot of formal verification, it's really, really important that we get this exactly right for every case. There are some operations in LLVM that are missing in SMT-lib and vice versa. And also there's the fact that SMT-lib constraints are declarative. So they don't have this imperative structure, they don't have an ordering, whereas LLVM IR, of course, is imperative. So I'll talk about how we rise to those challenges through an example. So this is the same constraint we saw before. Hopefully you aren't getting too tired of it yet. But here's a translation of this constraint into LLVM IR. So I'll leave this up for a second so you can take a look at it, and I think the slides will be posted later also. But in this constraint, each one of the operations from the, in this program, each one of the operations from the SMT constraint have been translated into an LLVM function application. So for example, the first two lines here, ZXT, the zero extension, that corresponds to the zero extend function applications that were in the original constraint. And as you go through here, you'll see almost a one-to-one correspondence between LLVM function applications and in the constraint. There's one important difference, which I've outlined here. And this is the part of the program that corresponds to the division in SMT-lib. And you'll see we've converted the division into 3 lines here. What's going on here, we're doing the division, we're then comparing the divisor to 0, and then doing a select based on that. And this is how we handle undefined behavior that I mentioned before, where in SMT-lib, division by 0 is a fixed value depending on the divisor. In this case, it's -1. But in LLVM, it would produce undefined behavior. And so we have to have these extra instructions to handle that. But once we have those, we get a function in LLVM that has the same semantics as the constraint. And we define the same semantics as meaning that the LLVM function returns true if and only if there's the LLVM function returns true on some inputs, if and only if those inputs would satisfy the SMT constraint. And if there are no inputs for which the LLVM function returns true, then the constraint is unsatisfiable. So we've gotten the translation down. Now we get the part that's nearly for free, the part that already exists, the LLVM optimizer. So I broke this down into different passes because I think there might be some interest in that. First, we do inst combine. And this simplifies the expression quite a bit. I won't go through every line here, but I'll point out one thing is we have 2 umul with overflow intrinsic calls here. Those correspond to the 2 assertions that we had in the LLVM. So in each case, we're doing a multiplication with overflow, and then we're checking that the second element in the vector to tell us whether or not overflow occurred. Then we do global value numbering. That lets us get rid of one of those. And then finally, a final run of inst combine simplifies everything away. So the LLVM optimizer started with that function through these 3 optimization passes. It simplified everything away and was able to conclude that this function always returns false. And now we just have that very simple last bit, the translation back to SMT, the backend translation, which gives us this SMT constraint that asserts false. And this, as we saw before, Z3 can solve almost instantly. So to look at what's going on overall, we started with a complex constraint. We translated it into a complex IR function. We applied the optimizer, got a simpler IR function, and then we translated back into an SMT constraint. And the final constraint is much simpler to solve than the original. The other thing to note is that in this example, because the original constraint took 10 minutes to solve, and it's a relatively small constraint in terms of the number of lines, the time it takes to do translation and optimization is very small relative to the original solving time. So in this case, it almost doesn't contribute at all. It's almost negligible. But in general, that might not be the case. If we have a really huge SMT constraint, then translation and optimization could take some time, and we have to offset that against the solving time of the original. So we've evaluated slot on the standard SMT lib benchmark set to see whether this speedup that we've observed in the example I showed you translates to a speedup on average. And we've tested it on 3 logics, one for bit vectors, one for floating point numbers, and then one for mixed bit vectors and floating point numbers together in one constraint that includes conversions. We tested it with 3 SMT solvers just to see whether the optimization is specific to a solver or whether it's more general than that. And we asked 3 questions. So the first is whether we can now, with slot, we can solve constraints that solvers timed out on. So those are constraints where we set a fixed timeout, and then at the end of that timeout, if the solver hasn't found anything, we say we don't know. So if we can solve those, that's a big improvement for users. We want to test what the average speedup is. And then the last thing I'll talk about is which optimization passes from LLVM contribute the most to the speedup. So we find that we can increase the number of solvable constraints by a substantial amount with a 600-second timeout, which is kind of a standard timeout or a common timeout for applications like symbolic execution, where you have many constraints that are run like within 1 hour, for example. We increase the number of solvable constraints by 9 to 14% for floating point numbers, up to 67% for mixed constraints, although there are fewer of those overall, and between 15 and 18% for bit vectors. So overall, this means we have hundreds of constraints that slot can solve that a solver on its own could not, that are enabled by compiler optimization. This is a graph of the speedup. I've broken it down into different original solving times. That's what's on the x-axis. The reason I did that is because of the phenomenon I mentioned earlier that the optimization and translation time could be substantial in this factor. And so one of the phenomena that you see here is that as the original solving time is growing, the proportional speedups are also increasing. There's a bit of variation, but in general, that's the trend. And that's because when the constraints are small in original solving time, then the optimization and translation time starts to become a bigger proportional contributor to that. But as constraints grow, the solving time is growing very unpredictably, even exponentially, whereas the translation time is growing roughly linearly. So then we want to investigate which LLVM optimization passes contribute the most. This might be kind of one of the most, the more interesting question for what conclusions we can draw from this. And the thing we realized as we did this is that SMT constraints are a lot simpler than programs. So there's only a single function, which means we don't need to do any of the inter-procedural optimizations. So that's 10 passes we don't have to worry about. There's no memory operations. We've decided to translate in a way that translates all variables into LLVM registers. So we don't need to do any passes that have to do with memory operations. And there's no branching. Everything goes into one basic block. This has to do with the way in which SMT constraints are unordered. And so we can get rid of any passes that optimize branching. There are 17 of those in the LLVM optimizations. And then there are various other reasons. There are some passes that have to do with particular backends or debug info. And those we also don't need to consider because they aren't relevant to the SMT problem. And then finally, we disable vectorization, which the LLVM optimizer sometimes would do on translated constraints. Because when we do backend translation, if we convert back to a vector, we'd basically have to undo all of the vectorization, and that would just slow everything down without providing any solving benefit. So there are 8 passes left, and they're basically the relatively simple ones. And it turns out that it's really the simplest LLVM optimization passes that are contributing the most. So the most effective passes are inst combine and global value numbering and reassociate. So these are really, to me, it's a bit surprising. These are by far the simplest passes that we have in LLVM. And these are the ones that are making the most difference for SMT constraints. And this suggests that solver developers could learn something from this work and apply some of the passes that exist in LLVM and other compilers to solvers to help improve performance. There are a few things to mention here. One is that what's simpler in the compiler context isn't always simpler in the constraint solving context. And so we use portfolio methodology in which we run both a solver and slot in parallel and just take whichever result comes out first. And this creates sort of a sieve where one handles some constraints well, the other handles other constraints well, and overall we observe a speed up. All the values I presented, I think I've mentioned this a couple of times, included the overhead that's involved in doing translation and optimization. And usually that's not a huge contributor. As you can see in this table for the small constraints, this is a table that shows the proportion of the overall time that's contributed by the overhead of translation optimization. So for the smallest constraints, it can be substantial, but as the constraints grow, it's quite small. There's one additional thing we might want to do. So far, I focused only on bit vectors and floating point numbers, which I think we're all familiar with. But SMT-lib also defines theories for mathematical integers that can be unbounded and mathematical real numbers. And so we realized that, so if we wanted to apply slot to these theories, we have to take one additional step, which is to convert these unbounded things, integers or real numbers, into bit vectors or floating point numbers. This turns out to be a much harder problem than I originally thought, because in order to do that, you have to pick a width. And that means you have to impose a bound on the original constraint. And it turns out that from some theoretical results in mathematics, as you can see in this table, there aren't theoretical bounds on SMT constraints, except for linear integer arithmetic. And in fact, in most cases, they're undecidable. So that means we have to kind of guess a bound and hope that it's right. And then at the end, check whether we were right or not by comparing the satisfying assignments. And so there's a trade-off in picking that width, that if we pick a bigger width, the solving is slower, but we're more likely to pick a width that's wide enough to represent the value, right? And if we pick a smaller width, then we're less likely to be right. So it's more likely that the width isn't big enough to represent the computation, but it's faster to solve. And that's what's shown in these two figures. And so to balance that, I won't go into details about this, but we have an abstract interpretation strategy that will be appearing in PLDI this year to infer the bounds on these constraints. And we find that by combining this with inference with slot, we can speed up nonlinear integers by between 1.5 and 2.5 times. And then even for some real constraints, we can have a substantial speed up, although that's harder because floating point semantics are complicated. So overall, I think the conclusion that we drew is LLVM optimizations can be applied outside the compiler context to speed up constraint solving and maybe in other uses also. The passes that we found, it's the simplest passes that contribute most to the speed up. And so I think that solver developers could learn from this. We've been looking into the simplification heuristics within the solver Z3 to see if anything from the optimization passes can be imported into a solver directly to help speed up the solving. There are some complications involved in that because we have to sort of break down in more granularly than just inst combine, for example, which things contributed the most. So we need to, there's some future work in that direction to be done. We might also be able to adapt in the other direction, so adapt SMT solving heuristics to the compiler optimization world. That's another future possible direction that we haven't really explored yet, but it might be useful in some cases. And then finally, one thing I'm very curious about after the MLIR workshop yesterday is whether we can create a new MLIR dialect to represent constraint solving, and whether that could make this process even more efficient or allow even more users to take advantage of constraint solving and other static analysis tools. And then finally, one thing we'd love help with, if anybody is interested, is to extend this strategy to arrays and strings. Those are simple in one sense in that there are LLVM operations for most of the array variables, but on the other hand, they face the same bound inference problem where we don't know the length of the array in advance in the SMT world, but we would need to in the LLVM world. So thank you for your time, and I'm happy to take any questions.
Yep.
Hello. Do you know if it matters in which order do you apply the optimization pass of LLVM to simplify the satisfiable theorem?
Yeah, it's a good question. So in terms of correctness, it doesn't matter because, well, barring bugs and optimization passes, it doesn't matter. What we've done in our implementation is we ran we took O3's sequence of passes and just took away all the ones that are irrelevant. So we run them in the same order as O3. We tried with just inst combine once, and that produced a lower speed up, but it was still speeding things up. The order of, say, inst combine versus global value numbering, we haven't done any experiments on that. It might be an interesting thing to try.
Okay, thank you.
That one went first.
Very interesting talk. Thank you. I was wondering, you said you run slot and the regular solver in parallel, and then you take whichever result appears first. When you looked at the cases where one or the other was faster, did that give you an intuition when it's worth trying to apply LLVM's optimization and when it's not?
Yeah, that's so thank you for bringing that up. I guess that's kind of a direction we have in mind for future work also. In terms of intuition for when it works, it seems that there are cases where LLVM wants to change numeric operations into bit operations. So it wants to introduce things like bitwise AND, bitwise XOR. And those tend to be worse for solver performance. But that's a very high level thing, so it's difficult to implement that into constraints to pick in advance which one. And there's also just a lot of data. There are more than 100,000 constraints. So I'm sure there are other patterns that we'd like to look into in the future. But that's the level of intuition we've gotten so far, but we'd like to look more into it.
Hi, Benjamin. Thank you for the great presentation. So I had I wanted to ask if you have thought of using knowledge of the compiler that is not visible in the IR. So what I was thinking is integer ranges and known bits, which LLVM is quite good at. So I was thinking that basically the compiler internally may know a range for a value that is then not visible in the IR. And as far as SMT solvers are, it might be very helpful to assert the additional facts that the compiler knows internally. So have you explored that? Is it an idea that?
Yeah, so we have explored that. Some of the SMT solvers, especially CVC5, actually implement something that's very similar to LLVM's the range inference. For known bits, not as much as far as I know. So that might be something where we could do it. But for the range inference, I think all the solvers I'm familiar with implement something more or less similar. So they don't, I think the avenues to implement that in a solver might be more limited.
Yes, just to follow up. So I was thinking that LLVM's range inference is probably better, or maybe some overlap. So if you could get some constraints from the original formula, add them to the LLVM compiler as metadata, and then extract the ranges and the known bits back, that maybe would be work.
Yeah, it's definitely worth trying.
Thanks.
We have time for more questions. Keep them coming.
Yeah, hello, and thank you for the talk. I would like to ask if you ran into any correctness issues when using LLVM optimizations.
Yeah, thank you for this question. So when we started this project, we actually started this as a compiler testing project. Our idea was that this might be a source of inputs that could expose bugs in the compiler. And we didn't find any. So we ran this on, it's more than 100,000 benchmarks, and we haven't found any compiler bugs yet. I think the reason for that is probably because the optimization passes that are involved are the simple ones. And the operations we're doing in the SMT world are relatively simple operations, no memory, no branching, none of that would invoke the more complex, more likely to be buggy passes. So I can't, based on these results, guarantee that these passes are bug-free, but we haven't found any. And we got sort of correct results for every benchmark that we've tried so far.
So maybe a follow-up. So you optimization classes. Like, do you? So maybe one of the question is like, do you think that it would be possible to externalize some of the patterns that Unbound uses into like solvers, or generally have them be like pluggable into solvers or like into other optimizers?
Definitely. That's kind of my hope as a future work from this. We started with translating to IR because that's kind of the simplest way to take advantage of the passes. But definitely in the future, I'd like to use the pass information that we have from LLVM outside to either implement it directly in a solver or make some kind of high-level description where you could implement it in lots of different use cases.
Okay. And final one, have you considered the equality saturation as have you considered equality saturation as a source of patterns?
Oh, yes. In fact, there's some existing work on generating SMT solver simplification tactics using equality saturation. There are a couple of works on doing that in an automated way. So that, I think to the extent that that would be useful, it probably already exists in solvers, but maybe it could be extended with some additional things like input from LLVM optimizations. It's possible.
Okay, that's all we have time for. Thank you, Benjamin, again for the talk. Round of applause.